As experimental techniques have grown from the top of the laboratory bench to the large accelerators of the today, the basic components have changed vastly in scale, but only little in the basic function. More important, the motivation of those engaged in this type of experiment has hardly changed at all. Wolfgang Panofsky, Contemporary Physics. Accelerators and particle explosion. We've been following a historical progression, learning about the developments of the modern physics starting from the late 1800s, working our way up now to be our 1930s. And then came World War II, was kind of the hiatus, not a hiatus in the scientific development or technological development, but physicists were busy with the war effort by and large, and so pretty much nuclear and particle physics research per se, especially theoretical research, shut down. The war had a big influence in a lot of ways. First of all, a lot of very bright physicists were brought together in the United States for the Manhattan Project, which was the development of the atomic bomb, and that was really a project in the technology and engineering. It really wasn't a project to develop any understanding of physics. There were a bunch of physicists there who are helping in this project. One of the things that happened was that these people who normally were separated geographically were together a lot of time, and they were talking and brewing ideas so that after the war there was a real explosion of both theoretical and experimental development. Wow. There were other aspects of the war. For example, radar was developed, and the technology and devices that were used for radar ended up being very applicable to making an experimental physics apparatus that was much more accurate and useful than what they had before. On a political level, I think the physicists had demonstrated a certain value to the US government for the national security purposes. There was an element of the prestige also associated with science that was developed during a war that led to a lot of funding and a lot of public support for the physics community and it lasted a long time after the World War II. I think today the situation is somewhat different, and in the future lecture we will talk a little bit about the shifting role of the particle physics in the world of the science and science funding. But certainly, right after World War II, it became a big science. Lots of money became available from the US government. Large institutions and laboratories were constructed, which of course had a big impact on the kind of developments that were possible when people were trying to continue their study of the nucleus and the subnuclear particles. Natural radioactivity is what people had been pretty much using through the 1910s, 1920s, and 1930s to study what was going on in nuclear physics. So you take some sample like uranium and you hold it next to the detector. Or perhaps you go up in the balloon and you use cosmic radiation, naturally occurring radiation. Naturally occurring radiation was good enough in the 1920s and 1930s, but it was not high energy and people wanted more energy. Why was that? There were various reasons. One of the reasons came from the quantum mechanics itself. The laws of the quantum physics, the laws of quantum mechanics, Heisenberg's uncertainty principle in particular, say that if you want to look at something very small, you need more energy. There is a trade-off. The smaller you want to get, the more energy you need. It's not at all an obvious fact of the life. It's not a classical idea, but you might visualize it in the following way. If you think about water waves have a certain wavelengths associated with them. It's a distance from one peak to the next peak of the wave. As water waves propagate, you can change the wavelengths of the light. For instance, If you are jiggling on the pond and you make a little wave, if you jiggle with higher frequency, with more energy, and the wave carries more energy, the waves tend to scrunch up. They have a smaller wavelengths. In general, you want to look at the small object, you need a small wavelength of light. The smaller the wavelengths, the smaller the object you can detect. So, waves with a big wavelengths will go past a duck, and the duck will just bob up and down, but the wave won't be perturbed. But if you have a little short wavelengths, then it will bend and reflect, and you'll see some shadow image of the duck behind it. It is the same way with the particles. The higher the energy that you put into your waves, and of course the quantum mechanics says everything is both wave and particles at the same time, the higher the energy. Consequently, the higher the energy, the better the microscope you have. So, if you are looking to understand subatomic particles, if you want to look at the smaller and smaller objects, you need higher and higher energies, right? There is another argument, physics argument, for why you would like a high energy collision or event in order to look at new things. It's Albert Einstein's E=mc². If you want to produce a particle with a mass, it requires some energy, the mass times the speed of light squared. That's how much energy you need. The speed of light is a big number. You square it and it's a huge number. You need a lot of energy to produce a new particle of nature, so the more energy you have, the more particles you can produce. If you are looking for more and more exotic particles of the higher and higher mass again, you'll need higher energies. I'm going to be talking about their energies quantitatively, although we won't be doing any math with them, but it's just nice to compare energy scales. Energies can be measured in various different unit systems. Particle physicists tend to use a unit called the electron volt, an EV. And never mind what an electron volt is, it doesn't really matter, it's just a scale for measuring energies. 1 electron volt is a rather small energy. It's a kind of energy that an electron might have if it's sort of sitting in a molecule, and that's a kinetic energy that it has. Yes, it's sort of a typical chemical kind of energy. That's 1 electron volt. A million electron volts and mega electron volts is how we abbreviate that. So a million volts a million electron volt is an large M, small e, large V, M. So MeV is how we abbreviate that. Also, a mega electron volt, that is sort of the more typical energy of a proton sitting inside of the nucleus. It has a million electron volts of the energy just rattling around in there, inside of the carbon atoms, a carbon nucleus or something. The rest mass energy of an electron is 500,000 electron volts, a 500,000 electron volts. So that means E=mc². If you wanted to produce an electron, then you need a half a million electron volts of energy. Wow. Unfortunately, you can't just produce an electron by itself, because you can't just produce one negative charge in nature. Yes, charge is conserved. Yes, charge is conserved. So if you want to produce a negative charge, you also have to produce a positive charge. You produce an electron and anti-electron together. Yes, this is a remarkable idea that led us to the creation of the particle in the machinery in the post-war era. If you pour energy into a small region of the space by slamming a particle into a target or some other similar mechanism, if you put energy into a small place, E=mc² says you can create a particle out of that energy. Energy can be converted into mass, yes, because on the left side of the E core is large E energy, while on the right side of the E core is mc square. So E and M is compatible. It's like a matter-antimatter annihilation run backwards. When matter and antimatter annihilate, they produce energy or photons. But if you bring photons in, you can create an electron and positron, and they will go flying off. You can detect them. They will leave the tracks in your detector, and that's how you could create antimatter in the laboratory. That's right. In the 1920s and the 1930s, people were trying to create what is now called a particle accelerator. It was a mechanical device to create a small particle like a proton or an electron with a lot of energy. You could smash that into a target and then see what came out. What kind of particles have you made? There was some successes even in the pre-war era. There were various devices that people came up with. For example, Mr. Van de Graaff invented the Van de Graaff accelerator. You may have seen this in the science museum or even sometimes in the high school physics classes. It usually has a tall post with a rubber belt running around it. Yes. And there is a big metal ball at the top. Yes. I've seen it at ELTE under ETH. Yeah. You charge it up with just static electricity, and if you touch the things, your hair stands on its end. If you really charge it up big time, you can get 1,000,000 volts on a Van de Graaff, and it starts to spark. What's a spark? It's really a lot of electrons traveling and jumping off the things. And those electrons have about 1,000,000 electron volts of energy. If you have 1,000,000 volts and one electron jumping off, you get 1,000,000 electron volts. 1,000,000 electron volts. So the Van de Graaff accelerator was actually designed not for the science demos, but to accelerate particles. Really? I didn't know that? I have had it. Okay, I did have it, this one. 1,000,000 electron volts is enough. If you pour that energy into the nucleus, you can sort of excite the nucleus. So if you are studying the nuclear physics and trying to understand how the protons and neutrons fit together, it's a useful kind of energy. But if you really want to go deeper than the protons and the neutrons themselves, if you want to look at the fundamental particles, the constituents, if you want to see what the proton and the neutrons are made of, you need much more than the 1,000,000 volts. The Van de Graaff technologies kind of got stuck at the 1,000,000 volts because it starts to spark at that point. It's really hard to prevent the sparkling. It's hard to get higher energies. There was a big breakthrough made by an American physicist named Ernest Lawrence. Ernest Lawrence was a big, tall, Midwestern physicist. You know, usually when I introduce some famous physicist who gets a Nobel Prize, I always say, a really smart guy. Ernest Lawrence was a fairly smart guy, but not one usually characterized as a genius by any means. He was just a go-getter. Who was politically savvy and had big ideas. He could organize folks and get money, and he had some good physics ideas. He invented the idea of a particle accelerator, but really, I don't think he did the work. I think his graduate student did most of the day-to-day practical development work. But Ernest Lawrence did win the Nobel Prize just before the World War for his development of the device called the Cyclotron. The cyclotron was a sort of the prototype of particle accelerator, which has been advanced and improved. Nowadays, we have devices that are kind of the descendants of the cyclotron that we still use to do particle physics research. Here is the idea of a cyclotron. If you want to speed up an electric charge, such as a proton or electron, what you need is some voltage, such as a battery. So you take a battery. Don't try this at home. And if you were to take a screwdriver and drop it from one end of the car battery to the other, you'd get a spark. It's very dangerous spark because it could cause a lot of damage. You'll get about 12 electron volts of the energy because it's a 12 volts battery. So imagine setting up a big high voltage batteries and you're sparkling across it. That accelerates the charged particles. Now, here is a trick that Mr. Lawrence came up with. Suppose you have some high voltage batteries and you get sparks across it. And then, when the spark reaches the far side, you have a little hole for it to go through, and it enters a region where there is a big magnet. What we knew already from the previous 100 years of physics research in the electricity and magnetism is that when you have a charged particle and magnet, it goes around in a curved path. Yes, it goes in a circle. So you accelerate this particle and then it leaves the battery region and it goes into the magnet region and it goes around in a half circle and then it comes back. Now the trick is to reverse the battery poles. Flip positive and negative. So you accelerate it on its way back again. It's as though you are whacking the charged particle every time it reaches the central region, and then it reaches the magnet and goes in a semicircle and comes back. It's kind of like a kid on the swing, right? You give him a little tap and he takes a swing and you just wait for them to come back. Then you give him another little tap. Each time he came back, you tap him again, and each time he gets more and more and more energy. He swings farther and farther, and more energy is created. That's exactly the idea of the cyclotron. It's a cyclotron because these things are going around and around in cycles, getting a little bit more energy each time. So you don't need super high voltage anymore. That's going to spark all over the place. What? So all you need to do is a bunch of little taps in the resonance. Okay? You have to tune the frequency of the taps just like the kind of the swing. If you just shake them, they don't go faster and faster. You have to tap them at just the right natural frequency. The only potential problem is just as with the kid on the swing, each time around he makes a bigger swing. At a certain point, your magnet runs out of steam and it leaves. Basically, you are limited by the size and strength of your magnet. In the early days, in 1920s, these things were the size of your fist. In the post-World War II era, when there was some big money involved, these things began to be housed in giant laboratories. There were gigantic magnets and the energy just kept getting bigger and bigger. I have a quote from Mr. Livingston, a graduate student of Mr. Lawrence. Dr. Livingston has asked me to advise you that he has obtained 1,000 volt protons. He also suggested that I add UP. This is a telegram from 1931 in the Nobel Prize winning work that first developed the cyclotron. So these were the protons. They were accelerated up to the 1 million electron volts and then they would go flying out the end and you have a beam of protons, which you can do whatever you want with. You can aim them at the target, like Mr. Rutherford had been doing with his naturally produced radiation, and study the atoms and what makes them. So, after the World War II, Ernest Lawrence was able to gather a tremendous amount of the funding This was the beginning of the big science in the United States. It was a government-financed research laboratory. Everybody wanted an accelerator, but not every university could afford one. So the idea was to centralize, to build a couple of national laboratories, and people from all sorts of different places in the United States could go do their research and use the accelerator. There would be a dedicated staff to run the machine, so each physicist didn't have to learn how to design and build a cyclotron on his own. Then he could collect his own data with his own experiment and go home and analyze it. There were various laboratories that started cropping up in the United States. Mr. Lawrence's laboratory was called the Radiation Lab, or the Radiation Lab. It was the most sophisticated and had more and more funding. Right after the war, the energy reached to 200 what? How can I read it? 2 billion electron volts? Yeah, so there is a 8 numbers after the 2 electron volts. Now that's a very special number because of the pion. Remember Mr. Yukawa, who had predicted the existence of a new particle of nature way back in the mid-1930s? He had even estimated the mass of the pion, which was, according to his calculation, about 100 or 150 million electron volts. When you take the mass and multiply by the c square, you need about 100 or 150 million electron volts to produce one pion. So if you've got 200, you have more than enough. You take your protons, smash them into the target, and you should be able to get some pions coming out. That's how we discover the pions. Basically, not through random cosmic radiation, but through the actual creation of these particles in the machine. Right.